All right.
We good?
I'm just going to do a quick intro. Welcome, everybody. This is the second to last student lecture. We've got two presenters today who are going to give a joint presentation on YOLO. Take it away.
All right. Thank you, Dr. Brigetti. Good morning, everyone. My name is Major Derek Worth, and co-presenting today on this topic is Major Jeff Choate. We are going to be uncovering and sharing the YOLO algorithm. All right, so during our presentation, we are going to basically split this up into two parts. I'm going to start off by explaining what YOLO is, kind of sticking to a high level, how to use it, what it is, how do images come in and go out. And then Major Choate will take over with a deeper dive into the architecture, explaining how YOLO does what it does. And then if we have time at the end, I've got a training and deployment demo and kind of walk you guys through using YOLO. And perhaps even at the end of this, you might be motivated to somehow apply YOLO to your research. So what is YOLO? We've kind of mentioned it a few times in class. Most of you already know it is an object detector. It stands for you only look once, because that's literally what it does. It looks at an image once and then it produces predictions, which makes it much, much faster over its competitors, like RCNN, for example. The other models are, most of the other models are two-stage, so that they have to iterate multiple times over the image, and they perform things like region proposals and region alignments, and they do that many, many times. While YOLO sends its image through a convolutional network that Major Choate will kind of describe a little more in depth later. But then all in a single pipeline, it predicts bounding boxes and class probabilities. So that's what YOLO is. Just a quick example of how that works. YOLO first takes an image in, and then it splits that image into an S by S grid. So this example has 27 by 27 grids. Then for every grid cell, and I'm only going to show a few here, they produce what's called objectness, or a confidence score. And then along with those confidence scores come the bounding boxes. So once you have the bounding boxes, then you can filter out the bounding boxes based off of the highest confidence. So in this case, the 0.98 was the highest confidence that this is a cow. And so that's what it predicted. All right, so that's like the really high level of like what's going on here. So I'm going to take a step slightly deeper. So how does it work? So I said YOLO splits the image into an S by S grid. So that's what you see on the left there. On the middle, it depicts all the bounding boxes. And actually, this is only a very small subset that's visually displayed here. There's actually many, many more. This is probably about 1% of all the bounding boxes that are detected by the network. But then the network uses what's called non-max suppression to basically get rid of all the bounding boxes that it doesn't think are actual objects. And then it hones in on the bounding boxes with the highest confidence. And so I'll talk about non-suppression on the next slide, which is right here. So what is non-maximum suppression? So on the top left image, you'll see that there are, so on the very top left, you see a car with 4 bounding boxes around it. So the network predicted those, and now you have to kind of filter out which of those bounding boxes is the best bounding box that describes or the location and size of that car. So what non-maximum suppression does is it goes through and it picks the bounding box with the highest confidence. And so, and then the end result is that car on the right. So if you continue following me in the bottom left, we've got a bunch of bounding boxes. Again, that's just a very small subset of the bounding boxes predicted by the network. But the very first thing non-max suppression does is it looks at the confidence of all those boxes, and if the confidence score or the objectness doesn't meet a specific threshold, then that box is thrown away. So what is left is the remaining boxes that have a high confidence score. And then the next step in the algorithm is it goes to the bounding box with the highest confidence. So in this example, there's actually two that tie for the highest. And then it grabs one of those, and then it runs a check on all the remaining boxes. And then it runs a intersection over union, which we'll talk about a little bit more later. But that is basically, so if I take this bounding box right here and I intersect it with this bounding box, which is our highest confidence, you find the intersection over union. And if that value that pops out of there is higher than a specific threshold, then that box is thrown away, because that tells the network, I already have a really good confidence that this is the box. And there's other box that overlaps it. We're going to go ahead and throw that away. And so it just keeps doing that until all you're left is those green boxes. So the input to the network is can be variable. Like you can put any image size into the network. However, that image size gets scaled down to a very specific set of image sizes. So the example I have here is, you've got n images, 448 by 488 images specifically, and they have 3 color channels. The thing about YOLO is that every image size that comes into the network has to be a multiple of 32. So it could be 480 by 480 or 512 by 512, and you just keep going. It can be, as large as theoretically you want it to be, but then it has to be a multiple of 32, and it gets scaled such that it's a square. So here's an example of a already scaled image. It's 640 by 640, which is a multiple of 32. And I'll talk in a little bit why 32 is such an important number. But for now, what does YOLO do with these images if they're the wrong size? So for example, this is a 1280 by 720. YOLO can still use this image, even though it's not a square, simply by using various methods. And so for this example, you can stretch it. You can stretch it to a 1280 by 1280, or you could even have shrink the width to make it the smaller image. And here's another strategy that could be used is this 480 by 800 could be padded on each side to make it an 800 by 800. So once it's got the image the right size, the network takes over and it does what's called a unified detection. So you grab an image, you split that image, like I mentioned before, into a grid of S by S grid cells. Each grid cell then gets assigned B bounding boxes. So in YOLO v3 and I believe up, the YOLO series basically defaults to 3 bounding boxes, but that number can vary. And then each bounding box.
Derek?
Yes, sir.
Quick question for you. So since it's multiples of 32, does that imply that each of those boxes is a 32 by 32 set of pixels?
Yes, I believe that's how the math works out. So yes.
Okay, thanks.
Exactly right. Okay, so each bounding box is composed of 3 sets of things. The first set is the X, Y, W, and H coordinates of the bounding box. There's a confidence, also known as the objectness, and the class probability. So if the network was trained to look for cows, chickens, dogs, and cats. That's 4 classes. You would have 4 blue cells right here. And the end result is a resulting tensor size of S by S by B times the 5 coordinates and confidence scores plus the number of classes that you have over here. All right, so I mentioned 32 is a really important number, and it's because YOLO does something kind of clever in order to accommodate a lot of different image sizes and object sizes within those images. And so it actually does detection at 3 different scales. So I told you it takes the image and it divides it by 32. It's actually doing a, it's scaling the image by 32 in order to find large objects. And if you look at the, for example, this cell right here, I mentioned that the center of the bounding boxes falls within each grid cell. Well, this particular cell, it can only be responsible for grid cells up to this size right here, because the center of this bounding box, if you grow it out any further, then the center of the bounding box will fall outside that grid cell. So that limits the amount of objects that this particular cell can detect. So what happens if you have like 3 or 4 or even more smaller objects grouped together, like maybe a flock of birds? Well, this scaling right here is not going to be able to detect that. So YOLO implemented 3 different scales. So if you look over in this corner, this cell, grid cell, can then detect even smaller objects. And then over here, the grid cell is even smaller. So go to the next slide. So these different strides, these different scalings are actually implemented at different parts of the network. But at the end, all 3 of these scaled images for different size detections are stacked at the end of the network, and they're all looked at once. So the stride is 32, 16, and 8. And so if you did not have a multiple of that, then the images over here wouldn't scale correctly. And that's why 32 is so important. So as an example, if an image took in a 416 by 416 image, the output sizes for those 3 different scales is going to be a 13 by 13, 26 by 26, and 52 by 52 respectively. And that will result in the large, medium, and small detections. So again, if you only had this large detection here, maybe you have a bunch of faces in the image, it would only be able to detect the large faces and not necessarily the faces in the background. That leads us into the next topic of anchor boxes. So for me, this was actually one of the most complicated or maybe abstract, hard to understand concepts in YOLO. But from what I've read, YOLO uses what's called anchor boxes, also known as priors, and and actually in version 1 of the algorithm, they didn't use this at all. They used just a simple bounding box prediction, which was computationally unstable because there are just too many different sizes to predict. So they actually copied this from one of, like in the second paper that they published, the authors mentioned that they saw in other algorithms like RCNN, they were using these anchor boxes, and they implemented it and actually stabilized a lot of their, and made their algorithm run much faster. So basically what's happening here is the network defines this anchor box, which is the dashed line on the outside. And each grid cell, so in this example, we're looking at this grid cell right here, and each grid cell is responsible for detecting or predicting, B number of bounding boxes. And so rather than trying to learn the shape, the aspect ratio, the size of a particular bounding box, the anchor boxes allow the network to just simply learn an offset from these anchor boxes. So in this example, the blue box represents the actual bounding box that's predicted by this grid cell. And the network, as Major Choate will explain the architecture, that Major Choate will kind of go into depth later, talking about the convolutional side, that is actually producing these T values. So TX, TY, TW, and TH. And now the network has to simply learn what those values are. And then that is, so the TX, TY are thrown into a sigmoid function that scales between 0 and 1. And that is added to the offset, the CX, CY, which is these directions. And then that allows you to find the top left corner of the grid cell. And then the B, W, B, H then allow you to find the center of that bounding box. So if all that didn't make sense, that's okay. This is a very kind of an abstract way of learning these bounding boxes. But in YOLO, I believe it's YOLO version 3 and later, they implemented default bounding boxes, which you see, or default anchors, which you see in the bottom right corner. Again, Major Choate will kind of talk about these a little bit more. But these define the width and height of each of the anchors, and then they're compared to potential bounding boxes. So if I can erase all this stuff, this is the calculation. I'm not going to go too much into it, but for each bounding box that is predicted by the network, it takes each grid cell has 3 anchors to choose from at 3 different scales. So if you're looking at the largest scale, that is this one right here. It will compare its predicted bounding boxes to the anchors. So it'll take 10 W, the width, and divide it by the anchor width. And that gives you the 1 over here. And then 10 divided by 15, and that gives you the 0.67 over here. And then it does that for each anchor. Then it normalizes those values. And then it continues to process them by finding the minimum, and then it gets the best anchor for all. And it basically follows this process, this 7-step process, until it gets this fitness score at the end. And that's what it uses in order to basically learn which bounding boxes to detect. In the initial release of YOLO, when they started using anchors, they were basically manually picking anchors, but eventually they found that they could just use k-means clustering to smartly find the anchors. So in this, on this slide on the right here, these are actually the k-means clusterings, basically the plots that I'm going to show in my demo of the various heights and widths of the labels that I trained the network on. So just to give you a quick preview, I don't know if you guys can see this. This is my webcam, and it's detecting things in real time. And what it's doing is it's taking these bounding boxes, and it's actually detecting 9 different classes. And those 9 different classes are what these kind of this histogram right here represents. And then it takes all those bounding boxes that I've trained my images on, it plots them across a height width plot down here, and then it uses k-means clusters to look for groups of clusters, and the centroids of those groups then become the bounding boxes that YOLO uses. Now, YOLO got smart and realized that, hey, these anchors can actually be improved. These are not the optimal anchors for the network. So they used an evolution algorithm, and basically they start with k-means clustering. They basically produce three. Well, in their paper they're showing here is 5 clusters. So they come up with 5 anchors, and then they randomly pick a subset of those, and then they vary the width and height in order to, and just by like a slight amount, in order to try to find a more optimal set of anchors. And then they basically run the metrics, and if the metrics say that this randomly set of new anchors is better, then it throws away the old anchors and it retains the newest anchors. Otherwise, it just keeps the old anchors, and it does that on an iterative process during training. And I think the papers that I read said it usually iterates about 1,000 times. So that's kind of a big overview of what YOLO is and kind of what it does. So question for you guys, and feel free to just
Jeff,
come up.
Sorry, Derek. Before you get to this question, can I ask you a question about the previous slide?
Yes, sir.
So if you have a training activity, like you get a bunch of images and maybe you have some data augmentation, but you're running your training, this is saying, I think you're saying that each set of actual bounding box widths and heights will be unique to that training activity. Is that correct?
That's correct.
So if I train my YOLO and then someone else trains a different YOLO with a different set of images, we're likely to have different bounding boxes at runtime when we go to test. Is that correct?
Absolutely.
Okay, thanks.
And there's actually a lot more to these anchors, but I think for the scope of this presentation that we've covered enough. So the question is, my YOLO network takes in an input image of 640 by 640. So what are the dimensions of the output tensor? So if someone wants to kind of volunteer to, I mean, if you don't know exactly, maybe someone can just kind of come on mic and kind of walk me through how we would calculate these dimensions. Anybody brave enough?
Do you want to go back to the previous slide that had the formula, or are you seeing if we remember the formula?
How about, so I could go back to the previous slide, but how about I just kind of walk you through it then, since yeah, I just really touched on it once. So if you have a 640 by 640 image, then this image will then get split up into how many grid cells. We'll start there.
20 by 20? 400.
Yep. So yeah, that is exactly right. So and how did you get that?
Each one is 32 by 32.
Yeah, so you're dividing it by that 32. And this is, again, is for finding large objects. So this gets divided into a 32 by 32. And that gives you, like you said, 400. But then each grid cell gets 3 anchors, and the bounding boxes are predicted for each anchor, giving you 3 predictions per grid cell. So are we done? Is it just 400 predictions? So no, the answer is, and actually.
But you have to break it into 8 and 16 as well, right?
Yeah, exactly. All right. So yeah, we have 32, 16, and 8 for our large, medium, and small. So you would have a 20 by 20 times 3 anchors or 3 predictions per grid cell. You would also have a 40 by 40 by 3 predictions per grid cell at the smaller resolution. And then finally, you'd have an 80 by 80 also by 3. And if you do the math, that actually produces 25,200 predictions. Each prediction then has an X, a Y, a width, a height, and a confidence, along with the number of classes that you trained your network. So that's basically the basic math. And then
Hey, Darren?
the other, yes, sir.
On that last one, I don't know if you can go back. Yeah. So the 3 is coming from where? Are you having like 3 different proposed bounding box aspect ratios? Is that where that's coming from?
Yes. So let me
Like
just go back.
Like a
this.
tall skinny and a fat wide and a square, for example?
Yep. So
Okay.
the anchors, so for example, the large scale might have these anchors right here. I have this, and maybe this.
Square. Okay.
There's 3
so those
anchors.
Are your 3. Got it.
And then all 3 of those are applied to each grid cell. The network then matches its detections to these anchors using the process I described on this slide, using these equations. And then, yes, you get 1 prediction per anchor per grid cell. That make sense?
Yes, thank you.
All right. And then the other question I had was, how does YOLO eliminate redundant overlapping bounding boxes? So if I got a face here, and then it's predicting this bounding box and this bounding box and this bounding box, what technique is used in order to hone in on the best bounding box? Anybody remember what it's called?
I know it's the confidence thing. I don't remember. Is that right?
Yep, exactly. So each of these gets the confidence, and the highest confidence wins. And then they do what's called non-max suppression in order to eliminate the lower confidence boxes. So with that was kind of a high level overview of what YOLO is, and Major Choate's going to kind of go into the architecture next. So I don't know, Jeff, if you wanted to like take over since you got a couple demos.
Okay, there we go. Can you guys hear me now? And see me?
Yes.
Okay, so Major Worth has touched on it a few times, but there's been a lot of different versions of YOLO, and so you saw some of his slides talking about YOLO version 3. A lot of the stuff we talked about was like based on YOLO version like 1, which is where they came up with that grid concept, and as it evolved to YOLO version 5, which is what the structure I'm going to present here is, it's changed a bit. They've modified different parts of the network architecture, so it's not as simple as it was, but all those same concepts still apply, and we'll go through how we're basically applying a lot of the stuff Major Worth showed in some of the following slides.
Jeff, you got muted.
Alrighty, there we go. Got to focus on the right application. Got it. So one of the things to start talking about here is that object detection in general has 2 main approaches. There's a multi-pass, 2-pass, or multi-stage, 2-stage type approach. And then there's also the single shot stage like we're talking about here with YOLO today. The big difference in these types is that the 2-stage essentially does that region proposal. It says find different parts of the image to look at, and when you look at that part of the image, then classify it. And so some of those region proposal networks will go say like thousands upon thousands of different bounding boxes for you to look at and then classify each of those bounding boxes. And that can take a very long time. And that's why YOLO is so great, is that it does it all in a single shot. And some of the nomenclature I'm using here, we could probably get into semantics and debate if you're a hardcore object detection person of what backbones, necks, and heads are. But I did this to try and be a little bit common between some of the different architectures. When we look at the YOLO actual network later on, in its definition file, it only has backbone and head. However, the concept is essentially here where the backbone is the classifier portion. So you have a classifier that says this is what a dog is, and then you have a neck in between those, which is helping you aggregate those different features and make sense of them. Then you have a head at the end that essentially creates those bounding box predictions that Major Worth was talking about. Okay, there we go. So this is the YOLO version 5 network in its raw form. And to quickly talk about what Major Worth was talking about with that stride 32 and actually getting all that stuff down to that, the correct sizes, we can actually look at this and do that math. So when you look at these little blocks, there's a stride of 2, and when you multiply these strides of 2 together all the way to the end with a 640 size image, you get down to 2020 and 4040 and 8080 type of thing. So that's where it makes it nice and clean to see some of that stuff he was talking about. But overall, this network has those various different stages. It has a lot of the things we've talked about in the past, where there's skip connections, there's residual connections, and many of these different techniques. So you can see up here this bottleneck blocks essentially are put inside each of these C3 blocks. These bottleneck blocks have a stride 1, kernel size 1, followed by a kernel size 3 stride 1 convolutional layer, and that's in order to increase the speed as well as increase the trainability of it. And I'll get into some of that in a minute. But those are put here in the middle. And then the big thing you're kind of taking away from this image is that there's lots of different kind of skip connections, residual connections, cross-stage partial connections, and that's where the industry's been going the last couple of years. So here's those different sections of the network that I mentioned on the past slide, and let's talk about each of those a little bit individually. So the backbone is essentially a classifier. This is where at training time they actually break it out and they say, let's train this backbone on an image classification task. So they'll send it millions upon millions of images and say, classify these images. And then they take this backbone that's now trained and they attach it to the rest of the network. Some of the details about this backbone is that it uses these cross-stage partial connections where it breaks it out and sends half of it through the main detector here and then the other half through a partial connection all the way to the end to get concatenated back. It utilizes those 1x1 to 3x3 kernels in order to reduce the speed of just using a 3x3 kernel. And the big goal here is to basically find features at different scales and complexities. And here's a kind of a leading question for the audience. Can a CNN end with a dense layer and vary the pixel width height of the input image? Anybody? Yes, no, maybe so?
Yes.
Is it a trick question? It can. Oh, you're smart. Okay. So that's leading to this spatial pyramid pooling subnetwork. This network right here is a little different than the spatial pyramid pooling network from the SPP paper itself. SPP itself is able to essentially make the output of its network a constant size. So you can have a convolutional network right before it and then a dense network after it. It makes it the same size by essentially max pooling across the kernels, across the channels, sorry. So the output size is defined by the number of channels, not by the image size. The way they did it here with YOLO is a little bit different for YOLO version 5 in order to increase the speed and some of its accuracy. So it does vary its output, and so you'll see later on that YOLO version 5 doesn't have dense layers at the end. It has convolutional layers, but that's one of the things I thought was really neat that I wanted to portray to all of you is some of the stuff we learned about dense layers being at the end, and you can't really have those and modify your image size. There are some techniques to allow that, if you will. The other aspects of the spatial pyramid pooling subnetwork is to increase the receptive field and increase resilience to scale variations. Now, these both have their limitations, and if we have time, we might show you guys like what happens if you send in different sized imagery to YOLO, because you can send it imagery that's vastly different size, and the receptive field of those detectors at the end is very limited based on the pixels, not based on the percentage of the image, if you will. Okay, the next aspect of the neck portion of the network is called the path aggregation network. This is very similar to a feature pyramid network. The big concept here is that it takes features in from multiple stages of that classifier portion, the backbone, and it aggregates those features up and sends those features back down. In a feature pyramid network, it just sends those features one direction, but with the path aggregation network, it sends them in both directions. And so this is used in order to help expose the fine-grained localization information that's available at those high pixel density, high feature map layers, as well as to those top layers. And it also helps detect things at various scales. And yeah, that's the main concept of this one, is they attached it. It uses those residual type skip connections into that classifier portion of the network in order to understand at different scale. And then this outputs at those different scales in order to basically say, here's a convolutional layer, which is of a size 5 plus the number of classes times 3 anchor boxes. And that's how you're going to get your predictions, right out these convolutional layers at the end. And since there's 3 of them that attach to the different layers of this path aggregation network, you're getting these predictions at different scales. And each one of these is actually going to produce a different number of predictions because its feature map size that is input is a little bit different. Okay, the next thing we're going to talk about here is some of the loss function and intersection over union. So as Major Worth was talking earlier with confidence things, one of the ways that it calculates confidence is intersection over union, or also known as Jaccard index. Typically good for an intersection over union is 0.5 or higher. And the nice thing about intersection over union is that it's scale invariant. And you
Hey,
can
Jeff?
see from, yes, sir.
Can you pause for a sec? So these diagrams are white, at least on my screen, they're very hard to see what the formula is that you're showing. Are you running, is this PowerPoint or something else?
This is PowerPoint, yes.
Can you maybe go into the edit mode just so we can see this a little better? I think there might be like a screen issue because it keeps changing colors and stuff. I'm assuming that's everybody's seeing this, not just me.
Is that a little
Yeah,
better?
Yeah, I see that too.
A little
It's-
better?
It's kind of hard to read.
Maybe you could open up that image of the formula and zoom in on it so we can, maybe you can get it a little bit better. Yeah, that's a little bit, it was a little better. I think you're like overblasting the contrast of your screen, like it's too bright, maybe. I'm not sure
Okay.
how you change that in Teams.
Yeah. Well,
It keeps
the
flickering.
big concept is that intersection over union is dividing the area of overlap by the area of the union. And so later on, I've got a little code demo where you guys can see some of the actual equations if you want. And that's distributed with that Python notebook if you guys want to look at that. But the concept is you take 2 bounding boxes, lay them on top of each other. The part that's intersecting, you divide by the union of those 2 bounding boxes. And that gets you a portion, essentially, a fraction. So that's the top level description of it, at least. Yeah. And the reason for this is because it's scale invariant versus some of the other things. So another quick question for the crowd. maybe. What's the downside if we weren't using intersection over union and we wanted to use mean squared error on these bounding box parameters? And I've got kind of a hint image over here if it's not too blown out for people.
Jeff, I have a suggestion because you guys both have these slides, right? You and Derek.
Yes.
Derek, can you try
Yep.
presenting and then just, Jeff, you can just say next slide or something? Maybe it's just your
Yeah.
computer.
Wait.
Oh, go ahead.
Let's see. Because the next thing I was going to do is a quick code demo, so it might be better to just kind of skip to that, and I'll ask this question in a second too. So is this going to be super blown out too?
Is it possible
much
for you to
better.
switch into dark mode, Jeff? I think it's under view, maybe? I can't remember where it is. Is there, does anybody remember off the top of their head where the dark mode is for this? Because I think what's happening is your pixels are super bright.
Let's see. I can try and change the screen. Does that one look better?
Oh yeah, a lot better.
All right. Different screen looks a little better. Got it. Okay. Okay. So
Thanks.
start with this question. Anyone got any ideas why there's a downside to using mean squared error instead of intersection over union when you're trying to predict things? And I got a hint image over here on the right.
And so Jeff, just to clarify your question, the goal is to predict the coordinate of a corner of the box. Is that correct?
Yeah, so as we're doing the loss and cost functions, one way you could do it is say, hey, the x coordinate is predicted x minus the other x, that difference squared, or you could use that intersection over union type of equation, which is dividing the intersecting area by the union area.
Right, so what's the GL or GIOU? What's that one?
Generalized intersection over union. And so that I'll talk about with what the
So we'll
downside
just-
of U is.
We'll just ignore that one and just look at the IRU versus the L2 mean, or the L2.
Yeah, that it's a leading thing for why
Yep.
IOU is bad.
Right.
Okay, so
I guess I can see that the metrics are worse, but I don't know why.
well, yeah, so you can see here like the L2 norm or the mean square error is the same for all these, but do all these bounding boxes really look like one is good or better than the other? I think these two bounding boxes are much better than this one because like, hey, you missed half your thing and that type of thing. And so the mean square error is something that's one, it changes based on the size of the thing you're predicting. So if I had two small bounding boxes and I use mean square error, that would have a small loss. However, if I use two big bounding boxes and there was a small error in that might be a bigger loss, if you will, because you're using bigger numbers, bigger differences. However, the wrongness of your thing isn't that much more wrong because you had essentially the bounding box cover up 90% of the other bounding box, and that's still pretty good versus mean square error saying, well, you're 5 pixels off versus 6, and so that's much worse or much better. So the IOU is much more scale invariant is what I'm getting at. And then there's a downside to using IOU though, and I don't have a great hint for it on this slide, and generalized intersection over union is the thing that solves it. But can you guys think about what happens when the bounding boxes aren't on top of each other?
Divide by zero error.
It's not divide by zero, but it equals zero. So you're going on the right concept there. The top intersecting area is zero. The union area is still big, but your answer is now zero. So no matter how far apart your bounding boxes are, it's always zero. And so that's why intersection over union as a plain function to implement isn't a great thing. And so that's why they came up with various different other ones, which other variants of intersection over union, which are called generalized intersection over union, complete intersection over union, distance intersection over union, and those which give you some sort of a metric instead of just 0 when your bounding boxes don't overlap. And so I've got a quick demo here that you guys should be able to download, a couple little imports. The only thing you're going to have to do is change this image out to an image you want if you want to play with it.
Hey, Jeff.
Yes, sir.
Quick question on the IOU last bit there. Is the reason that you would want to prefer some bounding boxes to others, even if their IOU is 0, is because like one's like way on the other side of the screen and one's really close but just not overlapping any pixels yet? Is it kind of like we're trying to pick the closer box is still better than one that's far away, even though neither one's overlapping? Is that the goal?
Not necessarily. I think we're talking two slightly different things. So the intersection over union is simply trying to give you a score of a bounding box versus another bounding box. And if you're trying to do some of the stuff Derek was talking about earlier, which is like find the correct bounding box for your object, if you will, like, hey, you're trying to find a tall, skinny bounding box, but it's far to the left of your screen, and your like a square bounding box is right on top of your person, and your person's tall and skinny. Maybe that tall, skinny bounding box would be better than a square.
Oh, okay. So you're managing the shape and the positioning of it.
Yes, and so the IOU is just calculating a factor of how good the overlap is of two bounding boxes. And the generalized IOU can be used in order to say like, hey, this one is better than the other one, if you will. And it does do a little bit of that in YOLO, but I think it's kind of a non-issue due to the fact that like these grid cells are actually pretty tiny in the scheme of things, and the anchor boxes that they have extend past the edges of those grid cells. So the main thing that grid cell is being restricted by is saying the center point should be in my grid cell. However, the anchor box can be tall and like really tall or really wide around that grid cell in order to best fit the stuff that grid cell wants to predict.
Okay, thanks.
Yeah, but yeah, this is a really quick demo that you guys can download to look at some of the code in order to see like IOU is calculated one way, GIOU is calculated another way, and I have a really rough my personal MSE function that I did here to show you guys that some of the stuff changes a lot. So like you're comparing two of these boxes, one's small, one's big. They're not overlapping at all. That means the IOU is 0. And having a 0 as a loss function is not great because you don't have any information about where to go. However, you generalize it, you get some more information about how to take derivatives of that and say one's a little bit better than another. The mean squared error is huge. Then you go to this one. The IOU and the GIOU are the same thing. That's nice. The MSE is a lot smaller than the last one, but it's still pretty big MSE, and it doesn't actually have much of a meaning to us as humans. And down here you can see, hey, they're not overlapping again. That's 0 and 0 and negative 0.82. So this was just a quick little demo that you guys can take home and play with, changing the upper left, lower right parameters of that bounding box and see how IOU works yourselves. Okay, the last couple of quick things is some of the lessons I learned during my learning about YOLO, as well as talking some more about the training process and scalability of YOLO itself. So with this metric called mean average precision, I wanted to talk about that for a quick second because that's something that took me a long time to grasp as I read all of these papers. And what this is basically trying to tell you is that accuracy is a bad metric for object detection. You want to use this mean average precision to tell you if your guess is good, and you use it based on thresholds of intersection over union. In a lot of papers, you're going to see something called like MAP 0.5. And what that's doing is saying if the IOU is equal to 0.5 or higher, then say it's a good guess. So what that means is you put a bounding box onto someone's head, as long as the IOU for the correct bounding box for that person's head is 0.5 or higher, then you got a good guess. It's a precise guess. However, if it's less than that, you got it wrong. And you're also going to see something in a lot of papers that's MAP 0.5 colon 0.95. And what that means is they took that IOU value and every 0.05 increment from 0.5 to 0.95, they averaged all the different correct guesses you got on an image for your bounding boxes together. So that makes it the average mean average precision, which is a mouthful. But that's the thing I kind of wanted to communicate to people is this is very useful for helping like rack and stack different object detectors. And so my question for the crowd here is, why is accuracy a bad metric for trying to say one object detector is better than another object detector?
Are you asking why is straight up accuracy of the classifier like, hey, this is a dog or this is a cat? Is that what you're asking? Versus the one you just presented, like mean or average mean, average precision?
Yeah.
Okay, so it's regular accuracy versus average mean, average precision. That's your question, right?
Yeah, pretty much. We can restrict it to a bounding box, but yeah, the concept is if you got a bounding box on somebody's head a little bit versus a certain amount type of thing.
Like, Brett,
I'm gonna
Brett,
kind
you
of
took
take
a
a
step out.
stab. I was gonna say, is it that you're not considering the area, like the box itself? You're just considering like you might get it's right, but it's only part of the object or something like that.
Yeah, basically that's it. Like when we look back at this example of like intersection over union, are you going to say this is a good guess if you can see the person's whole face? Not really. And also, if I just threw in a huge bounding box, you got it right, but now you're just kind of slapping bounding boxes everywhere. So it's not as right as it could be. And so the mean average precision is a way to utilize intersection over union in order to actually say that is a good guess of the person's face type of thing, that bounding box. So thanks for chiming in and giving an answer there. The last couple quick things to talk about here is the scalability of YOLO networks. So we kind of talked before about how you got all these different YOLO networks you can find. If you go to Google, you can find YOLO 4, 5, 6, 7, fast, and many different versions of it. The main thing we were talking about here for my part was YOLO version 5, and I wanted to point out that this is the definition file for the network itself. So it's a YAML file which says here's the 24 different layers. So there's actually hundreds of layers within this. If you remember back on the architecture slide, because a conv layer, that is actually kind of 3 layers. It's a convolution layer followed by a batch norm layer followed by a SILU activation layer. And a C3 layer is up to like 15 to 20 convolution layers within there with multiple residual and skip connections. And one of the things that the YOLO framework for version 5 does is it lets you set these depth and width multipliers. And so essentially you can say, hey, I want a small network or an extra large network in order to increase your accuracy or increase your speed. So there's a huge trade-off of accuracy in training and prediction speed. However, if you want to modify these, it's up to you. And they have small, medium, large versions that are already pre-trained for you as well if you want to use those. But the big concept is it's that same network architecture that's being scaled to different sizes by scaling the width, which is the number of channels, and the depth, which is the number of layers in a lot of these C3 subblocks. And that vastly changes the number of parameters from like 200 layers to 370 layers to like 3 million parameters to 30 million parameters. The last thing, and I think we talked about it a little bit earlier, was how the authors pre-trained their networks. The first thing they did was they trained their backbone as a classifier on hundreds of thousands and millions of images. Then they attached that to a neck and head in order to train the actual detection part in order to predict the bounding boxes. Some of the ways that they prevent overfitting is they have lots of different distortions for data augmentation on their data. They call that their bag of freebies because this does not affect your training, or sorry, it does not affect your prediction speed. However, it does increase your prediction accuracy and your prediction, yeah, basically. And YOLO version 5 is nice because it includes all this stuff in a nice little YAML file that you can set, and it'll do it all for you. And that's the main part of my talk. I think we have a couple minutes, so maybe Derek wants to take it back and look at a quick demo for his stuff, or if there's any questions as well while he takes it back.
I have like a general question. And maybe you sort of went over this, but the idea is that it's like computational efficiency. It's usually something that's like packaged for computer vision, where you're like, it's actively on, like a small processing platform, or is it something where this is more of a post-processing thing? Like,
yeah, this is meant. So YOLO version 5 was someone's basically implementation of all the past versions of YOLO onto GitHub, and they made it a framework unto itself, so you can easily go to it and download their train.py file onto your computer, train something, and then you could put that network that you built onto a phone potentially, because it's that fast. So did I kind of answer your question?
yep, that makes sense.
I've got a quick question for Derek and Jeff. How much more, in terms of minutes, how much more content you guys, not including questions, how much more do you have?
Yeah, so sir, actually, I was about to ask that. I know we're basically at the end of our time window.
Well, I was going to say that you're fine to keep going, but I do want to give them a break if you're going to be more than another 5 minutes or so.
Let's go ahead and take a quick break then.
Okay.
The demo could go long depending on questions.
Yep, let's do that. Let's do a 5-minute break so everybody can raise their hand. I'm going to start a timer, and then I'll call us back from break when the timer's over. All right. So just about over with the break here. Derek, if you wanted to set up your screen again.
All right.
Yep.
Yep. I'm back. Let me just put my hand down. Hand is down. Share my screen. All right. So, where's my slide at? All right. So now that we're back, I'm just going to give a brief demo. I thought about, I've kind of run through this multiple times, and originally I was just going to take you through like every step, and I think I'm going to still touch on every step, but I'm not going to like train a network on more than a handful of images, which is actually really a bad thing to do if you want it to be accurate. But I'm just going to give you an idea of like what steps you need to do in order to basically get a YOLO network up and running. And you can figure out how to do the labeling and collecting the images that you want to train on your own. So what you see on the screen here is the kind of the process or life cycle as defined by Analytics, which is the kind of the demo website that I'm going to show you. So, so the first thing you need to do to get started with this is just open up a browser and then type in YOLO v5. See, I was looking up anchor boxes a lot last night. And you want to type in GitHub. The top link is what you want by Ultralytics. And then you'll see that they have a, this is the repo that we're going to actually clone here in a little bit. But if you scroll down, you'll see a bunch of tutorials. So you can explore all these. They have different learning objectives, but the top one is the one we're going to concentrate on for this demo. So train custom data. That will take you to this page, which explains more in depth of what we're going to be doing. So if I don't cover it very well, you can like use this as kind of a, go back and review the different aspects. But what you want to click on is open in Colab. So you can obviously run this if you have a pretty good GPU on your laptop or your home computer. You can basically file and save this Jupyter Notebook locally, but for the demo, I'm going to run it on Colabs, so you can follow along. So Colabs, you got this Jupyter Notebook. If you're not familiar with it, basically presents you with kind of like an operating system. Off to the left is a folder. Here is the basic directory structure that you're familiar with. This is a Linux structure, and the folder that we're in is inside this content folder. So you have some sample data. And so what we're going to do is we're just going to go ahead and run this first step. Step one is install the requirements. It's going to pop up a warning that is saying, hey, this is not authorized by Google. This is something weird. Do you trust it? So just go ahead and hit run anyways, because this is coming from Ultralytics. And what we're doing is we're cloning their version of YOLO v5, which is a PyTorch version. Then we're going to change directory into, you'll see here in just a second, it's going to populate inside this contents folder, a YOLO v5 folder, which is what we're cloning off their repo. Then it's going to install the requirements based off of the requirements TXT inside the repo. And then it's going to, so let's see. Yep, so here's the folder. If you look inside, it's got requirements. Those requirements were installed. And then it's also spitting out at the end here what Colabs has presented to you as a kind of like a virtual GPU. So we're getting a Tesla T4, and that's what we're going to train on. Step two is to assemble our data set. So what you're going to want to do is pull out your camera phone. Here, actually, So we're just going to start from scratch. That was me testing out the camera last night. And about that one. Oh, shoot. Actually, I have something taken over my camera, and it's basically the demo. So basically, you're just going to take some photos. I already have a set of photos downloaded or captured. And you're basically going to go to, you're going to scroll down in your Jupyter Notebook, and there's a link right here to RoboFlow. So just take some pictures, and then you're going to come to RoboFlow, and then you're going to create a new project. So you're going to hit this Create New Project button. It will ask you to name the project. So I'm going to call it Lecture Demo. Name it whatever you want. Leave it as the default object detection. You can label your data with different methods such as classification and segmentation, but we're doing object detection. And then it wants at least a single label. So I'm going to put in a face, and then I'm going to do a create public. Then you're going to go ahead and hit the select files, and this is where you would go to your pictures and open a folder. Let me go ahead and kill this so I can actually show what that looks like. So camera. Okay, so I have my camera app open. I'm going to go ahead and take a picture. I'll just snapshot 3 pictures. I will go to those pictures. So here's the pictures I just took. I'm going to open that folder, which is right here to my camera roll. So here's the 3 pictures I just took. And then I'm going to basically upload these to RoboFlow. So I just select the folder, camera roll, hit upload. It found an INI file in there that it's just going to discard that, but it grabbed those 3 photos that I just took, and then I'm going to hit finish uploading. Then it's going to ask to assign these images, because what you'll find in annotating images is it's a very time-consuming process for humans to go and annotate specific objects. So this gives you the ability to assign to other members of your team. So for me, I'm just going to leave it as myself, assign myself those images, and now it's time to annotate them. Now you can use your own annotation software. There's a variety of platforms available. You can do it locally on your on your computer using one of those programs, or you can just come to one of these like online annotation tools like RoboFlow conveniently has for you. So again, I wanted to detect my face, and so if I wanted to just do my face, I could do this, or if I wanted to detect like my shiny bald head, I could kind of increase it, whatever you wanted to detect, and then you're gonna name it. And this you can label pretty much anything you want. So like if I wanted to detect doorknobs, I could put a label for that and call it doorknob. And so now I have 2 labels. And then if I go to the next image, I do the same thing. So take my bounding box, and then type in or pick face, because that's a face. And then I can again select my doorknob. And one more time. So as you can see, this takes probably about 3 or 4 seconds per object. And so like I was saying, it is not a trivial task to label photos. This is a time-consuming process. And so just for these 3 images, now I have labeled images. And so what you're going to do is you're going to hit the back button. Now your 3 images are annotated. You have 0 that are unannotated, and then you're going to go ahead and add 3 images to data set. If you have a bunch of images, this will actually split them. Right now, my training set will only have 2 images in it and 1 image in my test set. But you'll have a lot more images, and you can just kind of drag these bars to kind of decide how you want your set to be broken up into. So now that those have been annotated, you can generate a new version. So this, you basically go to the next step is in the process is to pre-process the data. So in this case, I'm going to go ahead and resize my images to 640 by 640. And as you see, it kind of like squished it or stretched it, depending on how you think about it. And I'm going to hit apply. The orientation, I'll leave the same. And then I'll just go to the next step, which is augmentation. Now, augmentation, you can add a bunch of steps in here. You can choose, and this is going to take all the existing images and apply variations of these augmentations. So saturation, you can change. You can kind of play around with some of these. Mosaic is always a good one to add in there, and maybe a rotation if you want your network to learn your face sideways versus upright. And then what I'm going to show you where I trained this on even more images, I had over 300 images with 9 classes, and I think I selected maybe 8 to 10 different augmentation techniques. And then what you'll see is I started with 3 images, and it's augmented it up to 7 images. And if you want more augmentation, I mean, 3 should be enough, but you'll have to pay for that. RoboFlow's got to make some money in their business model. So what it's doing now is it's applying those. So I hit done here. It applied all those augmentation and resizing steps that I just showed you. So here's the new images and their corresponding labels. As you see, they carried those labels forward, and those labels are now being stored in a text file, which I'll show you here in a little bit. So if you go ahead and export this, you can export it as a zip, and I'll just kind of show you what that looks like. Throw it into my downloads, save. So if I go to my downloads, here it is. I'm going to
Hey, Derek.
zip. Yes, sir.
Quick question for you. Is this RoboFlow just a generalized pre-processing stage, or is it specifically meant to be used with YOLO?
This is a generic pre-processing stage. RoboFlow does a ton more than just YOLO.
Okay. And do you have to know the target ahead of time? Like if you were building your own CNN and it didn't have a name yet because you haven't published anything on it, would you be able to use this as a pre-staging thing for feeding just generalized data augmented images to your network? Or do you have to pick one of their target architectures like YOLO, whichever version, or some other thing that they might have already included? Like I'm just trying to understand if it's more of a generic image.
That's a great question. So when you're creating a project,
mm-hmm.
You can create a project to do object segmentation, for example. But
right.
This RoboFlow is specific to object recognition. So whether you're doing classification, right. instance, or
sure.
Yeah.
The question I'm asking though is, do you have to know when you're saving your data off so that you can then go start training your models? Do you have to pick one of the like popular models, or like I saw you pick something and it said YOLO, and I thought that was strange that you have to describe which target architecture you're headed towards when all you're doing is pre-processing your data. Do you know what I'm asking? Like when you saved it out, I thought I saw you pick YOLO, which I don't know if that was just what you named it.
No. So RoboFlow does know about YOLO. So if I do an export, I can export in the format of YOLO v5 PyTorch,
mm-hmm.
Or I can.
Oh, you could just do like CSV or some kind of TensorFlow thing. Yeah. Okay. Cool.
Yes. Okay.
So you can do whatever you want. Thanks.
Yeah, yep. That YOLO v5 is just a text file, right? So you can change it if you want later.
Thanks.
So here's what it gave me. It gave me this zip file, and I extracted it, and it has a test and a train folder. If I had more images, it would have generated also a validation folder. And if you look inside it, here's my training data, here's my images, and here are the images that it created. And you can see that they are also reshaped. And then here are the corresponding labels. So if you open these up, you'll see that this particular image has 4 objects in it of class 0 and 3 instances of class 1, which I believe was probably my face. And then it gives you the X, the Y, and the width and the height of each of those objects. So that's the truth data that you're feeding into your network during training. Okay, so what you do is you export it, and so what I'm going to show you, you can use that to train locally on your laptop, like I just showed you, or you can export it a different way. You can export it as a RoboFlow, basically a link. So you're going to import RoboFlows. You're basically just going to copy and paste the contents of here. So it says don't share your key. You're going to see my key here in just a second. So please don't use it maliciously. So back to your Jupyter Notebook and Colab, we are going, now that we have our image, our data, we're going to go ahead and import RoboFlow. We're going to set our environment, and then we're going to copy and paste that code that we just got from RoboFlow right here. So this is just linking your Jupyter Notebook and Colab with the data that sits on RoboFlow's website on their server. So when I run this, it's going to go ahead and pull those 3 images, or those, I guess, those 7 images now that it's been augmented. And now those images are here on, they're right here. So test and train. So everything that you saw inside this folder is now, not this folder, but that folder that I had open earlier is now on Colab. Okay, next you're going to run this Python script right here. So you're calling Python on the train.py file inside the YOLO repository. And this Python file takes in an image size. We resized it to 640, so that's what I'm going to specify here. This shows 16 batches. I'm going to go ahead and change this to something smaller so you can guys see it. If I left it at 150, it'd be training for probably about 5 minutes. And then you specify where the data YAML file, which again is right here inside your data set folder. And this weights file here, this .pt file, is actually a pre-trained, the way I understand it is a pre-trained YOLO network. So you're not starting from scratch. If you were to start from scratch, your training would go for a very long time before it starts. What's that?
So that has all the weights in it. Yep.
Yep. Okay, so I'm going to go ahead and run that. And then what you're going to see is it's going to compile the network. Data set not found. Okay, so what I'm going to do instead, I think it's because it's giving me errors. Oh, it's giving me errors because if you leave this default, where was it? It's looking in contents, data sets, contents, data sets, lecture demo. Or am I messing up on here? All right. Data set not found, exception, data set not found. Contents, data set, lecture, demo, valid. Oh, it's looking for valid images. So, okay, so what happened here is it's not finding validation because I don't actually have a validation set in here. So what I'm going to do is I'm going to quickly back out. I'm going to go to the other model that I generated, which is this guy, not this guy. Sure demo. This one. All right, this one. So this is the one I actually spent quite a bit of time annotating. It has over 300 annotated images with 9 classes. And after augmentation, it generated 900 images in my training set, 30 in my validation set, and 11 in my test set. So this is much better to train on. So I'm going to go ahead and export this instead. Copy and paste this into RoboFlow. And I'm going to go ahead and import all those images. So yeah, what was happening was my other data set actually didn't have a validation set because of the data set was so small. So when this uploads, as you can see, it's uploading pretty quickly. Go ahead and run this stuff.
Let's say, Derek, one of the tricks I tend to use is just go in that data.yaml file and define them all as the same thing. So it's not true validation, but like the validation test will be the same thing usually.
Okay, yeah. Okay, so it worked this time. So you can see here it built that that architecture that Major Choate was kind of explaining to you before with the backbone, head, and neck. And now it's starting to train. Actually, it hasn't trained yet, but it's basically setting up caching images, and now it is training. So this will go. I set it for 10 epics. I found that 150 epics, which is what was defaulted on this Jupyter Notebook, was plenty to get a really good model trained. And like I said, that it should take. So there's the first epic. It takes about 19 seconds per epic. You know, you're looking at about 5 minutes. So while that's going, I'll just kind of talk you through the rest of the code. This cell block just starts up a TensorBoard, so you can visualize the training progress, the performance of the training. And then when you click on this code, you're actually going into YOLO, runs, train, and EXP. You're going, and then we're going to change this to EXP. Once that's done, it'll go into EXP. We'll just use EXP2 for now. And then you're going to change your image size to match. Again, we had 640 by 640 images, and then I'm going to run that after the training's done. And this last block of code will actually go through and take your test set and apply your network to it. And it'll show, so instead of these mushrooms, you'll actually see my face and the inferences or the detections that it made on the images of my face on the test set. Are there any questions so far? Okay, so the last step here, there's an export step that you can take your final file that is generated that holds the model weights of your trained network, and you can export it. So if I hit play here, after it's done training, and after it's done all the inferencing on the test set, it will actually export that file. I can save it locally to my laptop, where I can then either use the best.pt file, or I could, what I did is I exported it, and then I changed the file format to, so this is one of my other projects I'm working on, and this is the actual file right here. At the end of this training, I converted best.pt, best.pytorch, into an ONNX file. ONNX stands for Open Neural Network Exchange, and this provides a more general way of distributing your neural network so that it goes cross-platforms. So it's not just refined to PyTorch. You can run it on Keras, or in my case, I'm running it in OpenCV. Yep. So here are the inferences on my test set. As you see, it's picking out my head and a few other objects within the image. I trained it on looking for my Space Force patch, my rank, and then when I actually run the code, so this is Dr. Nikel's Afterburn engine. I basically have the YOLO v5 model imported. And so if I run this, it's going to run the engine, and it's going to basically grab that ONNX file and start pushing. It's going to use OpenCV to take over my camera, and it's going to start taking image data from my camera, as you can see right here. And now it is actually pulling inferences. So what you're seeing is all the bounding boxes, the grid cells, the anchor boxes, the architecture in action. And so if I take a step back, you can see in real time, it probably doesn't look like real time to you because of the latency of the network, but to me, this is like very crisp. You can see like objects floating around, trained it to look for my Stirling engine, maybe a stapler. And it's really fun to play around with. So I picked out my 3D printer, and as you're like playing around with this, you can, and you like understand the algorithm, what's going on, you can answer questions like, if I tilt my head, and this is kind of an open question for you guys, is if I tilt my head, is it going to still be able to detect my head? If I keep tilting it, all of a sudden it can't detect my head. Why is that? Any guesses? Or any
Because you didn't train it to?
Yeah, actually, that's exactly why. Every one of my training examples has my head upright. So as I turn my head, you'll see the confidence starts to go down, because what it's doing is it's using those anchor boxes, and it generated an anchor box, and it's taking the bounding boxes and it's fitting those bounding boxes, which has a specific aspect ratio, and it's fitting it to those anchor boxes. Whereas like my blue bottle, if I turn it, how come when I turn this sideways, it can still detect it when it's sideways or upside down?
So Derek, we got a question in the chat from Brad, and he asks, couldn't that problem easily be solved with data augmentation by generating rotating heads? And I thought I saw you actually doing that in the example of your RoboFlow. So did it not propagate in this version? Did you not do rotation in this version of your training set?
Yeah, so what you saw me do earlier was on a different training. I was only using those 3 images. For my 300 images that I labeled, I did not implement rotation, but absolutely. If you rotate it, as you saw in my data set, I did have pictures where my bottle was rotated. And so that is exactly the right answer. You could fix this by just either taking pictures of my head sideways, or you can do data augmentation where you do 90-degree rotations. So yeah. Any other questions? I see a hand raised. Ryan, you got a question?
No, I just totally forgot to turn off my hand from the break.
Oh, sweet. Okay, so
so here's just a side question. It's not about your presentation, but rather about the Afterburner. Was there a reason you needed to bring Afterburner into this? Is it just because it has the CV already running?
Yeah, I'm doing a lot of work in Afterburner already, and it was very easy for me to just like add OpenCV, capture image, throw that image into the network, and then get inferences.
Okay,
Um,
so it's
so-
not a necessary step. Someone else could have just used regular CV in a regular Python notebook or something.
Yep, exactly. And it goes back to that Onyx file. So you can run the model using PyTorch. That's what, by default, is what the Ultralytics version spits out. But you can obviously export into multiple formats, and Onyx is kind of the most generic and most in the research, in the literature, it showed that it's actually the highest performing model or version of storing the model, I guess. And then you can import that into pretty much any project. So that's what I have for the demo. Unless you guys have any questions, that's all I got.
So any questions from the class? Not hearing any questions from the class. That was really good presentation, really great presentation. I like, especially like the live demo showing in real time how that YOLO was working. So let's go ahead and thank our speakers. Great job today. I don't have YOLO running on my camera, so you're just going to see an unboxed face. You'll have to track me manually. The next thing that we're going to do is see if there's any course general questions. And then if there are none of those, we'll move into one-on-one project questions you guys might have. So any general questions, administrative, logistics, otherwise? We have one more presentation coming up. Edon and John Nash, I think, are going to be doing some interesting stuff on generative AI and reinforcement learning, right? So that'll be on Wednesday. So I'm going to go ahead and turn off the recording at this point because I'm not hearing any questions.